recording. So you started the recording, Pritam?
Yes.
Okay, so let me start. So welcome to lecture 20 on Riemannian symmetric space. Last lecture we have seen that this GKRN, this is the Grassmannian of K-planes inside Rn. This is really, we can identify with something called WK. And what is WK? WK is really, this is Q belongs to Sn, so that Q is equal to Q transpose, and this Q square, Q is equal to Q transpose. This is Q square is equal to Q. Just wait, actually, just open. Hello? हेलो, हाँ बोलिए। अच्छा ठीक है, मैं अभी क्लास ले रहा हूँ, बाद में बात करूँगा। ठीक है। हेलो, yeah, sorry for the disturbance. So GKRN is equal to WK. This is Q belongs to Sn, so that Q square is equal to Q, and this trace of Q is equal to K. So we have seen that this WK is a Riemannian manifold, and that gives a Riemannian manifold structure on GKRN. And we have defined this letter Q belongs to WK. So we have defined this RQ from Rn to Rn with a linear map. So that RQ on image of Q is really identity, and RQ image of Q perf is equal to minus identity. Okay, so now, okay, we have defined this something like SQT is really, this is RQ T RQ, and this is Q T belongs to WK. So we have seen that SQ belongs to this isometry of WK, and what I have seen, SQQ is equal to really identity Q. So today we want to really show that this SQ DSQQ is equal to minus identity. We need to show that. Okay, for that, so actually for that we need to really describe this tangent space of the Grassmannian. So claim this TQ WK, this TQ WK is equal to really X belongs to Sn, so that X of image of Q, this is really image contained inside image of Q per, and this S of image of Q per, this contained inside image of Q. So this is actually tangent. Ritam, are you able to hear me well?
Yes, Munada.
Okay, this is tangent space of WK at Q. So first we will assume this claim, and assuming this claim, we will really prove that DSQQ is equal to minus identity. So assuming the above claim we will show that DSQQ is equal to minus identity. Okay, so let this thing. Okay, so let X belongs to TQW. So what is DSQ Q at X? This is really SQX. Okay? This is because SQX tends to a linear map on SM to SM. Since SQ is linear. So this is the that. So SQX is equal to RQX RQ. Okay. Now I take this RQX RQ and you applied on any B. So that is RQX RQ, and B you can write that is really U plus U par, where this U belongs to image of Q. This U par belongs to image of Q par. Now the thing is, if you look at the description of RQ, this is identity on image of Q and minus identity on image of Q par. So therefore it will be RQX U minus U par. So this is same thing as RQ XU minus XU par because X is linear. Now if you look at the tangent description, X of image of Q and sits inside image of Q par, and X of image of Q par sits inside image of Q. For that reason, this XU, this will belong to image of Q par. And this XU par belongs to image of Q. So that is the now, since RQ XU belongs to image of Q par, this will be minus f of XU, and this is minus of XU par. So this is really minus of X U plus U par, and this is really minus of XB, and this happens for any B belongs to Rn, and so I get RQ X RQ is equal to minus of X. Now D sense D SQ Q X, this is RQ X RQ, but that is minus X. So this is minus X, X belongs to TQ W. So that means DSQQ is minus identity, thus minus identity on TQWK. This implies that WK is a Riemannian symmetric space. So this implies GKRN is a yes is a Riemannian symmetric space. Okay. So and I want to prove this claim that this TQ. Okay, proof of the claim. The claim this TQ WK, this is really X belongs to Sn, so that X of image of Q contained inside image of Q par, and X of image of Q par this to image of Q. Okay. Now let Y belongs to TQWK. This Sn is the set of symmetric matrices. Okay. So that means okay. So there exists a curve gamma from minus epsilon to WK with gamma 0 is equal to Q and gamma prime 0 is equal to Y. Okay. So now as this so-called gamma t belongs to WK, for t in between belongs to minus epsilon to epsilon. So I get this I will get three equations. Gamma t is equal to gamma t transpose. This is a so gamma t square is equal to gamma t, and third is trace of gamma t is really So I will call this three equation as a So now differentiating this A with respect to t and putting t is equal to 0, what we will get? We get this something like this. First, if I will put that, this will be really gamma dot 0 is equal to gamma dot 0 transpose. Second thing is, actually I apply this chain rule, gamma 0 and gamma dot 0 plus gamma dot 0, gamma dot 0 into gamma 0 is equal to gamma dot 0. And third thing is I will get trace of gamma dot 0 is equal to 0. Now I will use this information, gamma 0 is equal to q and gamma prime 0 is equal to y. So these three equations will give me something like this. X is equal to x transpose. So this will be qx plus x cube. No, not q. This is gamma dot 0 is y. Sorry, this is not x, it is y. This is really y is equal to y transpose. This is really y cube plus qy is equal to y, and the trace of y is equal to 0. Now I will call this thing as B. This is the equation B. These three equation I will call B. So let BQ is equal to Q belongs, Y belongs, X belongs to Sn. So that this xq plus qx is equal to x and trace of x is equal to 0. Okay, so that means what we have proved? We have proved this thing. This TQWK is inside BQ. So we have from B we get previous page we get this TQWK. This is subset of BQ. So check that this BQ is a vector space. It's a real vector space. It is easy to check. Now let us see what this condition means. Xq plus qx is equal to x. What does this means? So I am really taking xq plus qx is equal to x. This implies, okay, so qx is equal to x minus xq. So this is, you can really take x into identity minus q. This is really x into q power, where this q power is equal to I minus q, and this is the orthogonal projection. Orthogonal projection onto image of q power. So that gives you that this is really qx is equal to x q power. So that qx is equal to x q power. So that means and okay, let suppose v belongs to image of q power. So that means q of xv, this is really x q. Okay, this is actually qx of v, and qx is equal to x q power, this v, and since v belongs to image of q power, so v belongs to image of q power. This is will be what? So x v. That means xb belongs to really image of Q. Okay, so B belongs to image of Q par. I get this xb belongs to image of Q. Okay. So that means this implies x of image of Q par, this contain inside image of Q. Okay. Now so now let B belongs to image of Q. That means I use this relation Qx is equal to x Q par. So Q of xb, this is really x Q par of B, and since B belongs to image of Q, so Q par B is 0, so this is 0. So that means xb belongs to image of Q par. So this implies x of image of Q contain inside image of Q. Suppose thus what I'm suppose, and conversely, suppose this x of image of Q is really image of it is inside image of Q par, and s of image of Q par, this contain inside image of Q. Then this Q x of B, and you can write this B is really U par plus U par. This belongs to image of Q. This belongs to image of Q par. Now this, so if that is the case, Q, this is simply xu plus xu par. And since x of image of Q is inside image of Q par, so that means this is really, this belongs to image of Q par, and this belongs to image of Q. So this will be really what? This will be xu par, and this is same thing x Q par Q plus U par, and this is really x Q par. So this implies xq. So okay, this implies what? Qx is equal to sq par. So hence what we get? So hence we get this thing. Hence we get the equivalence of three things. This is qx plus xq is equal to x. This is equivalent to the condition qx is equal to x q par, and this three thing, and the third thing is equivalent to two things, x of image of Q which contained inside image of Q par, and this x of image of Q par contained inside. So now let v1 v2 let b is equal to really v1 v2 vk plus 1 and b an orthonormal basis bn o and b. So I really so that this v1 v2 vk, this belongs to, okay, this belongs to image of Q, and this vk plus 1 and this up to bn, this belongs to image of Q. I fix a basis, okay, and Q is fixed. Okay. So what I do, suppose okay, so let us call this three condition as a really C. suppose this X satisfies any of the conditions in C in the previous page. So I have chosen an orthonormal basis B, so that B is first k vectors belongs to image of Q, and last n minus k vectors, this belongs to image of Q, and I want to look at this matrix representation of X with respect to this B. So this thing is really, since X V1 will be inside image of Q per, okay, so that will imply that there will be something, the first k rows, actually first k rows will be 0. Okay, so there will be something star 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 here, and this will be happen for V2 also. Up to Vk you will get that like 0. And if you look at X V1 Vk plus 1, X Vk plus 1 is really lie inside this image of Q, so there will be something here star star star, and there will be 0 0 0. So this conclusion is something like this. X will be of this form. So 0, B, okay, not let us say it 0, C, D, 0, and this is a K cross K matrix, and this is n minus K cross n minus K matrix, and this is the thing. And this C is of this, C belongs to where? C belongs to M K cross n minus K. D belongs to really M n minus K cross Kr. That means trace of X, if you look at this thing, trace of X is equal to 0. So now we visit to the definition of VQ. Whatever is it? So VQ, this is XQ plus QX is equal to X. From there, actually we get this this condition, X of image of Q and subset of image of Q per, and this is the thing. And from there, we are concluding this trace of X is equal to 0. So hence we get, so thus we get this VQ is really X belongs to Sn, so that XQ plus QX is equal to really X, and this is really X belongs to Sn, so that QX is equal to XQ per, and third is thing is X belongs to Sn, so that X of image of Q is contained inside image of Q per, and X of image of Q per is contained inside image of Q. Okay. So this is the thing. Now, okay. So now I recall this. We have this Q naught. Okay. Q naught is equal to really I K cross K 0 0 0. This is the projection onto the space spanned by the first K elements of the standard basis. So I want to determine what is BQ naught. So BQ naught. So let X is equal to, you write this ABCD. So let us see that what this condition means. I will use this second definition. SQ is equal to, okay, so this Q, okay, so this Q, sorry, this Q naught X is equal to XQ naught per, and this is really, this is equivalent to the condition I 0 0, X is really ABCD. This is really X is equal to ABCD, and this q naught pop is equal to 0 0 0 I. Okay. So you have to partition this A, B, C, D in a very appropriate way. So here, for instance, it would be A belongs to M cross K, B belongs to M K cross M minus K, and C belongs to M N minus K cross K R, and D belongs to M N minus K cross N minus K R. So this is the thing. So now it is almost like a elementary matrix multiplication. So you will get this AB 0 0. This is really 0 0, and this is BD. From here actually you will get this whatever. I will get this A is equal to 0 and D is equal to 8. So this one condition is really giving me this thing, but I have another condition. X is a symmetric matrix. So this X, so this A B C D. So I am getting this A is equal to 0, D is equal to 0. So now 0 B C 0 belongs to Sn. So if and only if this B transpose is equal to C. Okay. Hence we get this BQ naught. You will get this is really 0 B transpose 0. So that B belongs to M K cross N minus K. So that means dimension of BQ naught. This is really K into N minus K. So now, so let okay. So let Q belongs to WK, any Q. Then there exists A belongs to ON, because we have shown that this action is transitive, so that A Q A transpose is equal to Q naught. So that means now let us see X Q naught plus Q naught X is equal to X. Okay. So this condition is equivalent to really, I can write this X in terms of Q naught. I can write A Q A transpose plus Q naught. Okay, in terms of Q naught, you really write A Q A transpose. This is X, and this is really the same thing as X. Now what you do, you really multiply A transpose from the left and multiply A from the right. So this is really right. So if you use this fact that A is orthogonal matrix, so this thing will be identity. So A transpose A transpose A is identity. So we will get this thing A transpose X A Q plus Q A transpose XA is equal to A transpose XA. So from there, from here you will get, so from above, you get that Q naught, okay, X belongs to BQ naught, if and only if this A transpose XA belongs to BQ. So here you will get that this hence we get, so thus we get this really, this is A transpose BQ naught A, this is equal to BQ. So that means dimension of BQ naught and dimension of BQ will be same. So hence dimension of BQ is equal to dimension of BQ naught is equal to really k into n minus k. But okay, we also know that this sorry, but TQWK contained in BQ and dimension of TQWK is really dimension of GKRN, and this is really k into n minus k. So both TQWK and BQ have same dimension. So hence we will get this GQWK is equal to BQ. Hence we get, so TQWK is really BQ, and this BQ is something like x belongs to Sn, so that x of, okay, so let us write all those things. XQ plus QA is equal to x, and this is x belongs to Sn. XQ is equal to QX equal to x cube bar. So x belongs to Sn, so that x of image of Q contained inside image of Q bar. So x of image of Q bar is really, so hence this finishes the proof of the claim. So we have really, no, is it okay? Or?
Yeah, it is okay. Yeah.
Yeah. So now this shows that so thus we have completed that that GKRN, this real Grassmannian of K-Planck, is a Riemannian symmetric scale. You can use the similar argument for GKCN, so you can do it on your own. So GKCN, this is 1 less than k less than n. So using exactly similar ideas, to that of GKRN, one can show that GKCN is a Riemannian symmetric space. For instance, there will be some trivial modification. For instance, in this case, what will be WK? WK will be really, this is really Q belongs to MNC, so that Q is equal to Q star, and this is Q square is equal to Q, and trace of Q is equal to K. And so he and you so replace this Sn by Hn. And what is Hn? This is x belongs to MNC, so that x is Hermitian matrix, so that x is equal to x star. So one has to really replace this On by Un, plus this On by Un, and action of Un will be on this Hn will be given by this thing really. U dot x is equal to ux x transpose, sorry, ux u transpose. So you have to do some trivial modification. X belongs to really Hn and u belongs to. So thus GKCN will be really the Riemannian symmetric space. And for GKHN, I have not really done that, but you can try that. But you have to really keep in one thing in your mind, that dealing with quaternion matrices is not really that easy. Okay, for instance, I have explained you once, a trace is not well defined. This determinant is not really well defined. There are some difficulties, but you can try that. I have not done that. Let us answer a question. Actually, one thing okay. Let us let us just answer the question which was asked in the previous class. Even though that was trivial, but let us clarify that point also discussion. So let us. I told you let this V. This is where be a real inner product space. So you can really. So what you do? You really fix. Is reconnecting. Are you able to hear me? Yes.
Yes.
I can't see Muna's presentation. Others are able to see, or it's my internet problem?
So I am sharing screen.
So you got disconnected in between, right?
Yes, yes.
Okay, okay. So I did not miss anything.
I'm sorry that it will be some. Are you able to see my screen?
Not yet.
No, no.
It seems that I have to really open this. HRI net connection is not showing now, and I fear that Geo thing. So are you able to see my screen now?
I don't see anything. I don't know about others.
No, sir, we can't see.
We don't see.
Like the same problem.
No, just wait. Okay. Annoy is HRI internet is back or not?
Actually, I am not in HRI
Okay.
right now.
Okay.
Yeah,
Sorry.
okay.
I forgot that you have told.
Thank you.
Muna, why don't you take a SIM card which has a better network?
So Geo I am taking here using. Okay, I will. Okay, I will try.
And talk to some people which network is better. So you can take that.
So now you are seeing my screen or not?
Not yet.
No.
இப்போ அது அந்த இது ஒரு இதுல கொக்கிலன்னு பரவாயில்ல இருக்கு காலையில் இருக்கு அதை மூடி வச்சுட்டேன்.
Do you see my screen now? Hello?
Yes, Munada, yes.
Yes, almost.
Yeah.
Yes.
Yeah,
Okay.
I can. Yeah. Yeah.
So there is some problem in my app, so I had to delete. So where was I? Yeah. Why did I lost the connection? So where was I?
I just
Yeah.
B is a real inner product space, then
Okay. So let B be a real inner product space. Fix an orthonormal basis. B is equal to this thing. B1, B2, Bn. And if you really fix a basis, then B is isomorphic to Rn. And this is the isomorphism. Phi is really phi is equal to 1 to n. Alpha ibi is going to alpha 1, alpha 2, alpha n. Thus, B is a smooth manifold. Okay. And if you take U, B, W in B, so this is really same thing as phi U, phi W and Rn. This inner product on B and this is an inner product on Rn. So let B belongs to B, then let P belongs to B. Then we know that TPV is really can be identified with V. Okay, so TPV can be identified with V. Now the question was asked last time that okay, so we define an inner product Riemannian matrix on this thing GP.
No, what is this one, Muna?
So what?
UW inner product at B is equal to phi U, phi W at inner product at Rn. How do you get this one?
Phi U is an element of Rn, right?
Yes.
So phi U, phi B on Rn. This is in means UW inner product on B. This is equal to phi U, phi W on Rn, right? So what is UWV?
I mean,
It
you
is
are doing
really
just basis change, right? Changing a basis
yes,
of
yes,
V, orthonormal basis of Rn, nothing else.
No, yeah,
nothing
it's
else.
taking a orthonormal basis. So it will be true for basis elements, then it will be true for other elements also.
So UW, you just write this thing alpha I, UI, alpha I, sorry, BI. This is beta I, VI, I is equal to 1 to n. And this is really what summation of I is equal to 1 to n, alpha I, BI, beta I. And this is same thing as phi U, phi W on Rn. Because what was phi U? Phi U is equal to alpha 1, alpha 2, alpha n, right?
Oh, fine. Sorry.
Yeah, this happens. This is good. So, so you have this. So let me. Okay. So let P belongs to V, then and UV belongs to TPV. Okay. So you define a Riemannian matrix at the point P. This GP of UV is the UV. So okay. So let us call this GB, Riemannian matrix on V. So this. So I told you that BGB is a Riemannian manifold. That is clear. But that is isometric to Rn. That was the issue. Why that is isometric to Rn? So what you do this? Okay. So to show that isometric, you look at this GRn. So phi p. Okay. So d phi p u and d phi pv. So this since pi is this is a linear map G d phi, so that will be really this will be phi u phi v, and this same thing as really phi u phi v. This is inner product on Rn, but that is really UV inner product on V, and this is really G of V. This is GB UB. As simple as that. So this will imply that I star G of Rn is equal to, this is not R, GB. And by definition, this phi is a linear isomerism, and we are borrowing this differential structure of Rn to V on by phi. So by definition, phi is a diffeomorphism. So phi is a diffeomorphism. Hence, this thing, this VGB, okay, sorry, VGB is isometric to Rn GRn. So this was not a difficult thing, but let us, so in this B, so let Mg and NH be two Riemannian manifold. Riemannian manifold. So then this product is also a Riemannian manifold. The product is a smooth manifold. So then M cross N is a smooth manifold. Now let PQ belongs to M cross N. Then you can look at this tangent space P, Q, M cross N. Then this is really isomorphic to this, something like TPM. You can plus TQM. This is a result in differential geometry. You can try this. This is not also difficult. So this is a isomorphism, vector space isomorphism. Now I can define a Riemannian metric on this product. This is G cross H, say, and I will define this PQ, and that will be it will have two arguments. For in the first argument, you will really, that it will be a tangent vector of M cross N, but I have this isomorphism, that is TP comma Q M cross N is isomorphic to TPM plus TQN. So I write this the UV and U prime V prime, where U belongs to TPN and U prime belongs to TPN, V prime belongs to TQN. So this is really GP U prime plus GQ V prime. So this U prime belongs to TPN and V, sorry, not GQ, this is HQ, not G, this is V prime, this is really TQN. And so that means this Riemannian manifold, thus this gives a Riemannian metric on M. So G cross S gives a, thus G cross A is a Riemannian metric on M cross N, and this M cross N G cross H is called the Riemannian product of M. Product of this really Mg and NH. Okay. Now what I will do, I will come back to our examples of symmetric space. So first thing is, so let M and N be two. I am not writing the metric, okay? So you know that B2 Riemannian symmetric space, okay? So then M cross N, the Riemannian product M cross N is also a Riemannian symmetric space. What is the metric, you know, and what is the thing as geodesic inversion I have to specify. geodesic inversion. This SP comma Q at P comma Q belongs to n class M is given by this SP comma Q is MN. This is SPM and SQN. Okay, so check that this is a check that SPQ comma Q is a geodesic inversion at a geodesic symmetry at P. Symmetry at P comma Q. So that means using this A, you can produce a lot of example of Riemannian symmetry. Corollary. So I want to really first write a corollary. So product of finitely many. Okay, I should write Riemannian product. And product of finitely many RSS is a okay. So using this corollary, one can give a lot of examples. Corollary, one can produce a lot of examples. Examples of RSS. Now this is the thing. Now I want to answer this one question which was asked by Tapendu. So let us build digression little bit. So this was the question once asked by Tapendu in the one of the previous lecture. Let let m is equal to really Sn minus 1 into say Sn minus 1. This is a Riemannian symmetric space. Okay. If you take PQ belongs to M, you look at the geodesic symmetry SP comma Q has really 4 fixed points. What is that? This is PQ and minus PQ, and this is P minus Q minus P minus Q. Okay, so now the thing is, similarly, if you take this M is equal to Sn minus 1 plus Sn minus 1, this is K-fold product, this is a Riemannian symmetric space, and this is product is K times. So one can show that any geodesic inversion in M as 2 to the power K fixed points. Okay, so now Tapendu asked this question. This is a sphere. Sphere is a compact symmetric space. Okay, I am saying compact symmetric space means topology is compact. Okay. So is it true that this happens only compact symmetric space or non-compact symmetric space? First, let us look at that thing. Then we will go to some interesting thing. Question.
No, what do you mean this happens? So what happens in case of
it has more
fixed
than
points
one
or what?
Okay, yeah. More than one fixed point. Okay.
But they can have more than one fixed point, right?
They can have more than fixed point, but he asked that in case of non-compact symmetric space, does it happen? So can you give me an example of non-compact symmetric space where it happens?
May not be true.
Not be true. Let us investigate a little. Okay. Is it? So can you give an example? Okay, no, this is a very example of non-compact symmetric space. Non-compact symmetric space means topology is non-compact. I am just writing, there is some space.
What do you mean by
Yeah.
topology is non-compact? It's a topological property. What are you trying to say? I don't get it.
You will see that. Okay, so you will really
Okay.
see that why I am saying this thing. Okay,
Okay.
there is some totality here. Okay.
You mean non-compact, but you don't want to utter non-compact type, is it?
Yes, yes.
Okay.
Where the geodesy inversion has more than one fixed point. So this is a easier example. Example is something like this is you can take m is equal to really Sn minus 1 into Rm or something like that, and you take this Pv belongs to m, then SPB comma V has two fixed points. You will get that. So this is really, but we can make this question little bit interesting. Okay. So this is a thing that you can get that in case of non-compact symmetric space also you get. You can get this question little bit make this question little bit different later. Okay, so we will divide or categorize symmetric spaces into three types, which will come later. Okay. So first is really Euclidean type, and this is really compact type and non-compact type. So Euclidean type is really your Rn. One prototypical example. Really, this is S1 minus 1. One prototypical example is Hn.
So Mona,
Yes, sir.
You are basically saying that Rn is a non-compact symmetric space, but it is not a symmetric space of non-compact type.
Yes, yes. So let us. So this is the thing I just wanted to this. So this is a warning here in this cell. So caveat or warning. So in this course, you will not really. So symmetric space of a non-compact RSS doesn't really mean that symmetric space of non-compact type. So therefore, this is really, for instance, Rn is not really thing, and so symmetric space of non-compact type is different from non-compact and symmetric. But for also you can take this thing actually. Symmetric space of compact type is really actually when you will see that in symmetric space of compact type it becomes actually compact symmetric space. There is a way, but for the moment, since I have not proved that theorem, so compact symmetric space is also you should take that is different from symmetric space of compact type. Okay. So non-compact Riemannian symmetric space doesn't mean that this is not equal to symmetric space of non-compact type. These are two different terminology. For instance, Rn is a non-compact symmetric space, but that doesn't really symmetric space of non-compact type. And compact type also you stick that compact Riemannian symmetric space is not equal to symmetric space of compact type now, but later we will prove that these are really same. Okay. So okay, so this is the thing. So you can ask this question: does it happen in this? So Rn, you see that Euclidean type, you will not really have any uh, SPU. If you take geodesic inversion in Rn, then it will have only one fixed point. So you can ask this question that whether geodesic inversion in symmetric space of non-compact type has more than one fixed point. Okay. So let us really ask this question. So let M be a RSS of non-compact type. So is it true that the geodesic inversion in M has more than one fixed point? So the answer is no. And this is a very thing that in a the reason is that in this case that you will get that exponential map is a global diffeomorphism map. So the whole manifold M is a really normal neighborhood, and I have told you that in normal neighborhood there can be exactly one fixed point. Okay, so reason is, let us, we will not have time to prove this theorem. Reason is, let P belongs to M, then exponential of this P, this is from TP M to really this M is a global diffeomorphism, and this, so hence one can regard whole M as a normal neighborhood. As a normal neighborhood, and therefore okay, so therefore SP has precisely one fixed point. So you can check this thing in case of this HN. So what is HN? Okay, so HN is a symmetric space of uncompact type. So now if you take this P belongs to HN, let P belongs to HN. So this SPB is really, this is minus B, minus 2 is VP and P. So suppose SPB is equal to V. So that means minus P minus 2 P P. This P is equal to, sorry, V. So that is really what I will get, 2V. If I take minus, really minus 2V P P. And this V is equal to really minus VP P. And you take this thing inner product of, sorry, not inner product, this bilinear product. So VP is really minus P, and this is minus P, P, and this is really minus 1. And C minus of BP will come from both sides. So this BP square, and this is really PP, and this is really minus of square. Now that will imply that BP is really either square is equal to 1. So that means B is really 1 or minus 1. So look at this equation. B is equal to, we will get P, or B is equal to minus 1. So this implies B is equal to actually P, or B is equal to minus P. But since minus P doesn't belongs to HN, so B has to be P. So hence SP has one fixed point. So I just want 5. Let me give 5 for 5 minutes, so that I will talk about this Poincare days. I will really.
Mona, I have a question here.
Yeah.
This is not very clear to me. That's why I'm asking.
Yes, sir.
that what is Hn according to you? It is those maps which preserve that bilinear form.
HN.
Hn, that last coordinate negative, that indeterminate form preserving maps. Is this how Hn being defined?
No, no. HN really, or X belongs to Rn plus 1.
Yeah, then you define that bilinear map, right? X1,
Here
X2,
is
Xn,
not
then
this.
minus. And then you
SK
look
minus
at
1
the
and
maps
X.
which, right, you look at those maps and then you take a part
No, in his case, is the level set
to the
corresponding to the value.
hyperboloid.
Yeah, it's the hyperboloid.
This is what you
No,
get, right?
hyperbole.
It's a upper sheet of the hyperboloid.
Yes, sir. Yes.
Right. Now, Hn has another description, right, using the group SON1.
Yeah. So that is really SO not n comma 1 mod SON.
Now, when you are using this upper description of Hn, according to me, you are defining a model. You are using a model. Now,
Yes.
suppose I don't want to get into a model and I want to define SP sitting inside this homogeneous space, this quotient. Have you defined that, or have I missed that point? Those, because some lectures I missed. Did you define SP using this, only these two groups, SO0 N1 and SON, without getting into any model?
No, actually, I have not defined. I have really.
Okay. Okay. But it should be possible, right?
So actually, sir, I'm sorry, but I am not getting your question properly. Actually,
My
so see
question
that.
is, according to me, my question is, according to me, Hn is what you have written below. SO0 N1 mod SON.
Yes.
Suppose the description of Hn which you have written above doesn't make any sense to me. Suppose that is the situation.
Yes.
It still has to be a Riemannian symmetric space. So there
Yes.
should be a way to define the map SP on this homogeneous space, on this
Yes.
quotient space. What
Yes.
is that SP?
We will come back to this later actually. So,
Okay.
So you this SP actually, sir, we have not started with a Lee theoretic definition. We will really there a Cartan involution will come many things.
I understand.
I have to develop.
I understand. So basically, according to you, Hn means based on this model.
Yeah, this model I am given this thing. Actually, this is the complete thing. Actually, so called if you and this see the thing is SON not n comma 1 mod SON is really we as a harmonic analyst we like that much, right? But as a geometer, I think they will like this thing. Do you get my point, sir?
Similarly, the Grassmannian see it as a homogeneous.
No, all I'm trying to say is,
Yeah.
I also like this Hn model because I can see it. There is no problem in that. The point is, in another picture, I will like to know SP. Now, who is the absolute picture? Because very soon you are going to define 3 models perhaps of the same space. So I'm saying that is the group model absolute? If that is, then it should be possible to describe SP in the group model. I made some mistake somewhere, is it? The whole
No.
wrong.
But it may be difficult to see how the SP acts, right? If you take that group model. Because here in this.
But working with that is easy. Okay, so I think that I should
just a minute.
here.
I'm not saying you have to do it. I just ask you whether you have done that or this is the way you are doing it now.
No, we will do that. We will do that later. That will come.
Okay.
So So the thing is, I should actually one thing I should tell you, all of you. Actually, I will not do Poincare this very in great detail, but SKR actually has given some lecture on. Actually, when I was student, he gave some lecture on IISc Kolkata. So you can ask him to actually if he will allow, then I can upload that. And you just read those things. I will actually just.
ட்ரெயினில் போகணும், இல்லை எக்கனாமிக் ஃபேரில் போகணும், இல்லை சொந்த காரில் போனால் 20 ரூபா காசு, 3 தான். அவன் இங்கேருந்து டாக்ஸி
போயிருக்காங்க.
அப்போ இது இவங்களுக்கு இந்த இதுபடி 3 ஆப்ஷன் தான் கொடுத்துருக்காங்க.
அது நம்ம பார்த்து
இல்லை அப்படியே ஓன் கார்னு கன்வெர்ட் பண்ணி கொடுத்தா.
Yes. So what I'm saying that you just read those. If you will allow, then I can upload that, or it is completely on him. Whether sir, will I upload that first lecture of your this thing?
If nothing nonsense is written there, then you can upload.
Nothing. How can be nonsense if you have written something? So so in the next lecture, actually, I will discuss these 3 models little bit. This hyperboloid model. This is called hyperboloid model, and this upper half planar disk model, and I will give some basics of Lie theory. So you are strongly encouraged to not to attend that if you know those Lie theory stuff. And then actually we will move to those Lie theoretic thing, actually this so-called Riemannian symmetric pair and all those things. So just then let us stop it today. Actually, I could not do anything about this. Okay, so let us meet in the next lecture then. So Tapendu is